All right, I'm recording now. So again, this is our plan. Last Wednesday, we built Clip from scratch. It was a really interesting project. We had some cool things to play around with. We had some really high accuracy when it came to text to image recall, really close to the Clip baseline from the original model, despite us training on 130,000 images instead of 400 million. So that was really interesting, and it helped us understand multimodality really well. But now for this week, week 3, this is probably going to be, in terms of AI, it's going to be our low level stuff. We're going to really pry open these models. We're going to learn how they learn and how they train. It's very mathematically inclined this week, but we're going to work on a project on Wednesday, which is building our own auto differentiation engine. And we're going to learn what that means. And there's also a bunch of tutorials on how to work with PyTorch code and maybe JAX. And we'll look at all that today. So again, I think everyone here has filled out this form. This is the Airtable. If you haven't filled out this form, please do so. This is how I could reach out to you and how you could get notifications for meetings, videos, slides, everything. I always post on the Discord and on the Notion. So I'm gonna leave this up for like another minute, but I think most of you already have this. Okay. And yeah, so here's our notebook for today. Make sure to copy the short URL and go to the notebook. We're gonna, again, discuss gradient descent and go through the mathematics of it. And we have some visualizations there. And also for the second half of today's meeting, we're going to do some like PyTorch exercises, some PyTorch tutorial stuff so that we can have a better grasp on how to use the tools we need for deep learning. Again, the syntax I wouldn't say is the most important bit. The most important bit is the intuition. Tools come and go, but the math behind it remains relatively the same. So that would be the main focus, just building our mental picture of what goes on in these deep learning frameworks. So copy the short URL. I'm gonna leave it up for another minute or two. And from there, we are going to, from there, we're just gonna jump straight into it. Okay. Make sure I have the right. Oh, and one thing before I start, the YouTube videos are up. I haven't posted them yet on the channel, but I'm still working on different things when it comes to the YouTube channel and specifics. Right now, I have them uploaded on my private, I made a private channel on YouTube, and you guys can see the videos on there for past lectures, and that's where I'll be posting most of the past lectures. So after this meeting, I'll post some links, and then I'll make everything more official. Right now, it's on my, a channel I made, but we also have an INIT AI Guild YouTube channel. Again, I'll send all these links out, but I'm just letting you guys know the videos are going to start being posted after every meeting. And also, yeah, throughout the week, any interesting things we might discuss. There are a couple lectures that I still have to go back on and record, like the CNN, just the CNN implementation. And I'd like to go over the clip loss function one more time. I'll probably record those and post it by the end of the week. But yeah, just letting you guys know that. Again, I'll post them on the Discord, but let's just go straight to it. Yeah, I'm sharing my screen. Okay, so this is our intro to gradient descent. Let me make sure. Okay, let's just run the first couple cells. These are just our imports and our random seeds so that we have, so we can reproduce each other's results. And again, we're going to talk about gradient descent. What is gradient descent? This is basically the fundamental algorithm that helps a neural network learn. It's basically, to me, the backbone of all of this modern AI. And yeah, again, we have trained models, but we haven't really inspected what goes on internally. And this week will be a lot of that. That's why it's very math heavy. And gradient descent, we basically calculate gradients, which are very much like derivatives. And this is, again, very calculus based, and we're going to see this. But first, let's clarify what weights and biases are. Basically, when we train a neural network, our main goal is to find the optimal value for the weights and the biases, so that our loss function, which is basically our calculation of error throughout training, can be minimized. So hopefully you guys can see how that can fundamentally be viewed as an optimization problem. So for example, in a linear equation, in linear regression, we have y equals mx plus b. We're replacing the m with a w for weight. And that represents the slope, which represents kind of the steepness of that line. And then what our gradient does, we basically ask, if we change this weight by a little amount, how much will the total error go up or down? And let's visualize this really quick. Just run these few cells. Here we're just creating a random sample of a standardized, normalized sample of 500 different data points. And this is what they would look like in a scatter plot. And our goal is to just make a linear regression line that best fits this line, right? And normally how we initialize neural networks, we randomly initialize these weights and biases to start with. Obviously, there's more science sometimes when it comes to initialization, but for right now, let's just randomly initialize our model. Again, in this case, our model is just a y equals mx plus b line. So here we're just randomly getting a weight, which would be our slope, and we're randomly getting our bias, which is a y-intercept. And we want to tweak these parameters until it perfectly fits this line. And by perfectly, I mean it minimizes the loss as much as possible. So here is just some random values. And now here comes the mathy part, right? So for this task of linear regression, we're going to use a loss function called MSE, the mean squared error. This is probably like the, I don't know, hello world of loss functions in neural networks. Basically what it does is we check the separation between our predicted values and the true values of the data set. So if we predict that a value would be here in this point where the mouse is, we kind of calculate the distance and we see how far it is. And again, our goal is to minimize our loss function. In this case, our goal is to minimize the distance between our predicted data points and the true values. So this is what what mean squared error is, the loss function, right? So we're getting the average separation basically. The reason we're doing yi, imagine that's the true value, y hat is the predicted value. We're doing the minus, and then we're squaring it. So what we're getting is like a separation. It's not negative, it's not positive, it's just a separation between the two values. And we do that for n number of data points. So we find the average of that. And again, our goal is to minimize that loss. So let's write down the formula. Let me check if, yeah, okay. So I think everyone can see here. So our formula is our loss is 1 over n, right? And this is the summation from I equals 1 to n for the separation between our true value and our y hat value squared. Someone joined the meeting. So right now, this is very simple, just math, right? If we're given 3 data points, like 4, 7, and 1. Let's do that in order. 1, 4, and 7, and we predict 3, 6, and 9. What we do is we find the separation between the two. So here, the separation, the true value minus the false value, or the predicted value, 1 minus 3, that's -2. We're gonna put it down here. -2, we square it, we get 4. Here we get 4 minus 6, that's also -2. We square it, we get 4, and then, well, again, -2, we get 4. We add these up. This would be 12, and then we divide it by our number of samples. We have 1, 2, 3 samples. So we divide by 3. This is a pretty easy average. I mean, 4 plus 4 plus 4, we know that's an average of 4, but we can say that our loss function for this instance is 4. Okay. That's just walking through that pretty quickly. But again, this is basically our function that we are measuring with a given x, and with a given x value, and then our weights and biases. So for this instance, it make it simpler. It doesn't make a difference overall, but if we flip around our y hat minus our y, just to make the math look a little prettier. But again, the results are the same, because when you square something, negative or positive, it will be the same magnitude. So what is our y hat in this instance? Our y hat is, again, that is the predicted value. How are we predicting this? We're predicting this with a wx plus b. So if we plug this in, we have our loss function for a given x is equal to 1 over n, I minus 1, n, and then again, we plug that in, weight of xi plus b minus our true y. This is MSE, this is our loss function. This is how our loss function is calculated. Yeah. So how do we remember that what we want to do is find the optimal weight and the optimal bias? Because, for example, if we're given, let me do this in a different color. If we're given these data points right here, right, we want to find a slope and the y-intercept that best fit this line, that best fit that kind of that data. So when we randomly initialize, let's say we're given a random W of 3.5 and a bias of like 4, it's going to be something all the way up here, right? So we kind of, per training, we kind of have to get it closer to this data and then fix the slope up. That's, in a way, essentially, that's what goes on inside the training of a neural network. But how do we actually tweak these values? This process is through gradient descent. So again, this is our loss function formula. If we want to find the partial derivatives of W and B, let me erase this and let's get straight to this part here. If we get our loss function, and with respect to W and B, it's the same thing, 1 over n, and then the summation of I equals 1 n, and here we have Wxi plus b minus the true value of y squared. We want to get the partial derivatives of Wi, of our weight and our bias with respect to our loss. So this is, in this case, partial derivatives, very base level calculus concept. It's probably the most important thing you have to get like kind of nailed down for this kind of algorithm. We have the loss function with respect to W. To derive this, this is like power, like the power rule, right? We send the 2 over, so it's 2 over n, right? We have the summation I equals 1 to n, and then we keep this true, right? This is our variable inside. So first we're taking care of the exponent. Actually, let me write like the power rule. In this case, I don't know, a of n is equal to n, or like the derivative of this is na n minus 1, right? So we send this forward 2 times. Let's actually do it step by step that way. We have 2 times 1 over n. Again, this is a summation. And then the a stays the same, right? So it's b minus y. This is now 1, but now we have to find the derivative of this internal function. Now, since we're doing this with respect to w, our internal function is x. So here, what's the derivative with respect to w? It's just xi. And we do the same with the bias. Now, the bias is, again, very much the same, 2 over n, summation of I equals 1, and here we just get left with the same thing, except without the xi, because this is with respect to b, not with respect to w. And I outlined these equations here in this little spoiler, but we're going to focus on why this is important. Why knowing this basically is the key to your model learning and generalizing. And we're going to show this through the code, and I'm going to walk through the code by hand so that we can more easily visualize this. So here in the code, in the notebook, I declare this MSE function. This is the same thing we have here, right? We're doing the average of the prediction minus the true value squared. And we're going to train our little model with, 26 epochs, just a small little training set just to show you guys what happens. And we're going to go internally here, and we're going to see what gradient descent is within training. And again, we're doing it, this is pretty manual. Again, we're going to see with PyTorch how this works. But if we run these epochs, right, basically what we talked about before happens. We're given a random line, basically, and our goal is to best fit this. So you see that the slope and the bias of the line kind of starts changing until we meet a point where our loss function is very, very little. Again, look at what happens when our loss function is high. This means that on average, the separation is huge between like a true value at 1.5 and then the actual value at 1.5, for example. By the time we get to epoch 20, epoch 25, our loss is really low, and you see that the line best fits that. So what happens here? How are we actually tweaking these weights and biases? First, remember, we're declaring our y prediction right here, wx plus b, and we're passing it through the loss with what we find and the true value. And so what we're doing is we're finding some kind of error. So this loss is a function for some kind of error. And we do this thing called backpropagation, where once we go forward, we do 2 things. We do a forward pass in training, forward, and then we do a backwards pass. This is backpropagation. Forward pass is when we make our prediction. Backwards pass is when we adjust our values based on the error that our prediction gives us, if that makes sense. It's a pretty intuitive thing. And that's what happens. In this case, it's just, you can imagine it as one neuron, but through the layers of a neural network, this is what happens multiple times. And here you see, we're going to update the weights. Remember, at the end of the day, what does a derivative tell us in calculus? Let's say we have some graph, and then we have, I don't know, y equals x squared. The derivative at a certain point, if we want to name this point right here, it basically tells us the slope at that specific point. And again, remember I said that gradient descent is essentially an optimization problem. So this is going to be a really interesting part. If you view, let's make a big graph. Let's just do it for the weight at this point. In this case, what is this function, right? If we strip all of this, like averaging out, and we replace this with our distance, and we replace it with a variable, we can kind of say that this function is loss equals, if we replace the y's with some variable, I don't know, t, it's kind of like a y equals 1 over nt squared. Here we're making this equal to t. So if we visualize our loss function, it is this quadratic representation, right? This is a y equals x squared graph. This is our loss. And remember when I said our goal is to minimize our loss. This is something we do a lot in calculus when we want to minimize the cost for something. You can also imagine the loss as a cost. When do we know that our cost is the lowest? In this instance, it would be when the derivative is 0. That means we don't have a slope that either that goes up or goes down. So our goal, again, if you imagine this is our loss graph for W, for our weight, and we have a weight at some point, we have a weight up here. We want to find our way down to this 0 point right here, as close as we can to it, because that's telling us that our loss is minimized as much as possible. So again, we have our weight right here. And here at this specific point in this graph, we have some slope. Let's say, I don't know, the derivative at this point, whatever, 2x. This doesn't write 1 foot. We know our slope here. So if our slope is positive, we know that, the graph is going up. If our slope is negative, we know it's going down. In this case, it's positive. And again, we have to get our weight lower on this graph. So we have to kind of take a step down in this case. Does that make sense? Okay. So if you look here, where we do the updating weights part, let's focus on the W. Remember, we have 2 parameters we're optimizing for. So the same way we're doing this here, I actually have a graph in the slides later that is going to show this. We're doing the same for the bias. We are taking the derivative. So the slope at this specific point, it's telling us, in this case, that it's a positive value. And again, our goal is to go down. So we're going to subtract and to go down. We have some learning rate. This is a hyperparameter in deep learning. You see learning rate here and you see epochs. When we did the clip, our learning rate was like 0.0001. This basically tells us how big our step down or up, depending, down, is. For example, here we have our weight and we want to update it. So we subtract our weight with the multiplication of our step size, our learning rate, and our derivative. The reason we're subtracting, again, we want to go the opposite direction of up. So we take a step down. If our learning rate was like 1, we take a huge step here, right? In this case, 0.1, let's say we take a little step down, and we do that for 1 loop. Then we try again. Now our weight is down here. We do the same formula. We find the loss. The loss should theoretically be lower at this point. And then again, we find the derivative at this specific point, and we take a step down. This is the fundamental intuition of what optimization is in a neural network. We want to, again, find the optimal weight and bias, the optimal combination that makes our loss as close to zero as possible. So again, this is our loss graph that the loss function creates just by nature of what function it is. In this case, MSE. So we do this a lot. This is how our specific weights change. So again, at the beginning, the weights were like random, which gave us this line. And through bit by bit optimizing our loss function, our weights kind of fit the line more clearly. Now, this is one equation. This is just a simple linear regression, right? But I want you guys to think in the instance of, let's see, in CNNs, when we worked with CNNs, right? Or let's stick to a normal neural network, right? We do our linear equation of Wx plus b, and then we apply an activation function on top of it. And let's think about the sigmoid function. Sigmoid. And then here we have this y. Or ReLU or any activation function to kind of change the linearity of the graph. Remember, y equals Wx plus b, that just gives you a line. But if we want to fit a data set better, for example, if the data is more kind of like this, we want to make the line non-linear to fit that data better and to better explain the patterns within that data set. When we do some kind of back propagation throughout all this, we find the derivative of the sigmoid function. And then if you guys remember, I think this would be a case of the chain rule. We do a bunch of derivations to optimize ultimately the W and the B. This is what fundamentally goes on inside each training of a neural network. And let me go back to the slides here so we could visualize this better. This is, again, we literally just drew this right here. This is the algorithm that minimizes the loss function. And I want you guys to think, whenever we are training a neural network, any model like that, our goal is to minimize some function that tells us how wrong we are. And again, fundamentally becomes an optimization problem. So depending on the task, we need a carefully crafted loss function. And depending on what loss function you use for a given task, this is kind of what you're going to get. So over here, this is an example of literally what we did right now of MSE. Right? In this case, we have two different weights and we measure the error. A good way to always intuitively visualize this is we want to get like a ball and we want, imagine like we have a ball here, randomly initialized. So we start here and then we want to roll the ball down. Our goal is to make sure that it rolls to a local minimum. This is another instance of a loss function graph, if you see it graphically. This one's a little more complex, right? Not everything's going to be as simple as this. Sometimes you have, I don't know, some weird graph like that, for example. And our loss or our optimized and local minimum, we end up finding here due to randomization. Let's say we start with our weights here and we do our back propagation. We're going to end up here. At this point, there is nothing that goes lower. We're going to stay here. Yes, we found a good minimum, but there is still overall in the graph a lower absolute minimum that we could have gotten to. So that's just, again, examples of making sure we use the right loss function for our given task. Here we have an example of loss functions. MSE, very simple, right? And again, we derived it, we worked it through here. If we focus on clip, what we built last week, it is something closer to this, the loss function that we have to minimize. Cross entropy, it's closer to this loss function. This is called KL divergence. These are all different loss functions that describe different tasks, because sometimes here we're trying to optimize like a regression task. So we want to find the best fitting line. But if we want to classify something, we end up with probabilistic outputs. So when we were classifying, if you guys remember with the CNNs, let's pretend this is like MNIST. We have 10 neurons. Each neuron gives us a probability that the input is a given value. So in this case, 0, 1, all the way to 9. And we have different probabilities. And then we pick the highest probability, but there is a ground truth as well. If this value is 7, we want to get our 7 neuron as close to 100% as possible. How do we do that? How do we measure that? Everything has its own loss function. In this case, we would measure with some kind of cross entropy loss. So in this instance, there's a lot on the board. Let's see what space. Okay, we still have space. So in this instance, this was just one neuron, one pair of weights and biases. When we think of a lot of neurons, if you guys remember just the MNIST had 784 input neurons. This is 784 different neurons. Each one comes with its own weight, and then we apply a bias on top of that. So we have a lot of weights to optimize. So calculating the derivatives manually like we did, it's not optimal because, well, that's very expensive. That would take a lot of time to do. And also, the way we end up doing this, we group the weights as matrices, and then we do a lot of matrix multiplication. CPUs aren't good at matrix multiplication. We want to optimize our code for GPU kernels. And this is kind of why we have PyTorch. It's the leading deep learning framework as of now. And it is what we call an auto-grad or auto-differentiation engine. And you see it in the name, it automatically differentiates across the neural network. Again, this is basically the power of PyTorch, why we use PyTorch. Otherwise, we'd be manually doing all of this in code for each neuron and having to keep track of it. This is an example of some PyTorch code. Here we have tensors. Remember, the tensors is like the main mathematical data structure that we use to represent our data. In this case, we just created a tensor of 1, 2, 3, 4, 5, 6, a two-dimensional tensor. 2 by n. Here, in this case, it's just a 2 by 3 grid. You can see it. This is like a matrix. Again, 1, 2, 3, 4, 5, 6. And yeah, there's just some addition between the tensors. Again, why do we actually need PyTorch? Again, you technically don't, but this would require low-level coding for these neural networks. And this is just an example of one just kernel. You have to deal with multi-threading. You have to deal with a lot of different things, a lot of different like memory management, a lot of things that make this suboptimal for actually training these high-level neural networks. So again, PyTorch, underneath the beautiful Python and NumPy-like syntax, we have all of these CUDA kernels that are making this work. And here, let's talk about the tensors. Basically, this is our way of storing the variables. So in this case, the parameters we have, weight, the biases, we store them in tensors, and we create these graphs. Again, I want you guys to think of the neural networks. Our goal, we go through different layers. all the way until we reach an output layer that we get some values for, and then we calculate a loss for it. And remember, we do that derivations. Hold on. We do the derivations of, from this point, from this loss, we do the derivations as we go backwards. That is our back propagation. And you know, we kind of have to visualize these as a graph. So this is just an example of a computational graph of different tensors. So here we have tensor A and tensor B. Added together, they create tensor D. And then same thing here. We do some multiplication. And when we do back propagation, we get the derivative of this y. Imagine this y would be the loss. And we find the actual local derivative of each tensor. And that's the thing. Tensors hold two values. We hold the scalar value, like the item, for example. That would be, in our case, with the weight. In this case, you know, whatever weight it may be. And then the grad is the actual local derivative, the local slope at that instance. Back propagation. Again, this is what we just talked about right here. So here we're having an input feature X, an actual output Y. This is just example of code. And when we reach this dot backward in PyTorch, this is where we automatically differentiate all of these equations as we go backwards. So for example, the derivative of e squared would be 2e. And then as we go backwards, we want to find the derivative of each component within this graph. This is the way we visualize this graph. You can see this is where the chain rule becomes really important. And this is what on Wednesday we will be literally manually building ourselves, our own auto differentiation engine, our own mini grad, and we're going to make a miniature version of that. Basically, again, a framework that will automatically compute the derivatives as we go backwards. And again, through this explanation, you see why knowing the derivatives of each parameter is very important as we want to minimize the loss function. And then and here we're just displaying the gradients. Again, the most important part here is all of that is done pretty much automatically just with the call of one function. And if you guys go back to the notebook, see if you want me to say. Okay. And here we're going to do the same thing, right? We're going to call some randomization. And we're going to declare X and the Y as two tensors. So the X value, instead of a NumPy array, it would be a tensor. Same thing with the Y. And our weights and biases, we will randomize them as tensors. And we're putting require grad. Why do we put requires grad? This is something we have to do so that PyTorch basically knows to compute the gradients of it when we do back propagation. It's not efficient to just to automatically assume that every variable that we have is meant to be kind of like meant to hold a gradient. But since we know that we're going to use the weight and biases, we have to optimize these. We require a gradient for these two parameters. And then again, we're declaring a 26 epochs and a 0.1 learning rate, our hyperparameters. And now we are going to do the same. Here we get the output, but we're going to do the same loop where we declare the forward pass, where we find the MSE, but here we call backwards. Backward, remember that is back propagation. This is basically this whole part and the updating, it's done automatically through the backward. And then, and then we update it ourselves. So torch.nograd means that this isn't going to affect the gradients. This operation right here is not going to affect the gradients. We're not going to hold it as, remember, Torch creates its own computational graph. We aren't going to save it as a gradient in that graph. We're just doing this isolated. So we update the weight and the bias. And then for the next round, if we keep the gradients over time, they're going to either, get really high or get really low, depending on the slope. So we want to zero the gradients for the next run. And then here we're counting the epochs. Here you see an upgrade of the loss. And here, it is just the same thing, a high-level PyTorch implementation of this same loop. But this time we're using the different classes. Here we have a linear class. We have in features 1, out features 1. So we're just putting in one X, we're outputting a Y. That's our model. We're defining the loss and the optimizers. You probably saw this when we did the clip model. Again, we use the criterion, we use an optimizer. What exactly is this? The criterion, you see it's nn.msc loss. So the criterion is our loss function. And optimizer is optim.sgd. The SGD means stochastic gradient descent. It is basically just gradient descent. Imagine it that way, right? We're using gradient descent, our algorithm to optimize the loss function. We're passing through the model.parameters. Model.parameters would be like the W and the B. And our learning rate will be what we declared up here to be 0.1. And here we're just reshaping the data so that it could pass through. But then here in this loop, we do a forward pass where we pass our prediction through our model. And here we declare the loss using the criterion, in this case, MSE, mean squared error. And then we do the backward pass. If you remember, we zero the grads, and then we compute new gradients as we go backwards. And this dot step does the update that we did up here manually. And we just, here you're just going to see per loss, per epoch, the loss. Again, you're just seeing how gradient descent results in updated weights and biases throughout training and how this leads to a better performing model. Now, again, I said we were going to do like some little PyTorch exercises and to learn kind of how to use the framework. Here, this is a bunch of different methods that we have in PyTorch. These are focused on tensor creation. So if you recall the code before, right here, torch.tensor, and we're passing two different arrays, mix them into a 2x3 tensor. That's how we declare our tensors. Zeros, this declares a tensor of just zeros across the board. .I, you could imagine this as the identity matrix. If you declare kind of, I don't know, .I of like a 3, you get a 3x3 matrix. It's just the identity matrix. Right. A range and lin space, these are to, I don't know how to explain it, to kind of find like the space and make like a 1D array of the space between each numerical value. So for example, A range, I believe it's by step. So we have, if you declare an A range of 4 with a step of 2, you would get something like 0, 2, 4, something like that. And then lin space, it would be more focused on the actual final value, and then the separation would be done by itself. So these two do kind of perform the same function. It's just a different way of us looking at it as programmers. Reshaping and manipulating. Well, if you guys, let's see, if you guys remember when we implemented, again, always going back to when we did our CNN lecture, when we implemented clip, we reshape if you remember when we did it with the MNIST data set, right, we're given a NumPy array, I believe it was of 60,000, 28, and we reshaped it so that we can add our color channel and have result of tensor of, batch 60,000, one color channel 28 by 28. This is what we do with reshape. And these are just different methods on reshaping your tensors. Again, in the notebook, we have different exercises, just fun exercises to like try out different methods and see how they work. Math operations. The most important thing here, I would say, is broadcasting. Broadcasting, you see it a lot when you want to perform some kind of mathematical operation between two tensors that aren't exactly the same size or shape. So in an instance where we have tensor 1, its size 3, 2, and 4. Let's do a better example. 3, 2, and 1. And then we have tensor 2, which is size 3, 2, and 7. If we want to add these together, this 1, we basically scale it to a 7, and we kind of act like this was a 7 all along. We can do the addition there. The two rules for broadcasting, either you have a 1, thus you can change the value to whatever fits the other, in this case 8, or they must be the same dimensionality. And again, we're going to have more concrete examples of this when we do our like little exercises. And then in linear algebra, if you want to do matrix multiplication, we did this when we multiplied the logits in our clip implementation. And we also transposed, if you remember, the dot T. And also today we're going to go over einsum. This is like the crazy multiplication and kind of like the dark, the dark skill of like performing linear algebra functions. We're going to see it through the notebook. And yeah, slicing syntax. Remember when we worked with the Dilbert, we had to get the CLS token specifically. Where was that in the tensor that represented the text? We had like the batch here, we had the sequence, thank you. And then we had like, so we had the sequence, we had the dimensionality here of the vector. So yeah, we keep these and we just wanted the first index of this one. So if you remember, we did this little operation here to be able to get the CLS token. This is the same kind of slicing syntax. You have to know the dimensionality of your tensors. And here we have stacking if you want to stack different tensors together or concatenate them. Again, we're going to go through them one by one. And gradient operations, this is what we talked about. Backward to perform back propagation, and then requires grad, whether our parameter requires like the gradient to be computed and to be handled in the computational graph or not. So if you guys can go to the notebook. Do you need the notebook?
Yeah.
Okay. I'll go back to the notebook, but if you guys can go back to the notebook, this is a short URL.
Oh.
Yeah. Go back to the notebook. Here we have some PyTorch exercises, kind of. Again, just to get used to, don't worry much about the syntax. Again, tools come and go, but the math and the intuition, make sure we can build that up. So here we have a couple little like exercises, problems to kind of solve. So first we want to create a 5x5 identity matrix using .I and replace the diagonal 0 to 4 using .arange. So remember, .I, what it did was compute the identity matrix, and arange kind of it kind of initialized a specific range for us. So let's go one by one in this instance. So here we will work with the identity matrix and declare torch.i 5. The 5 here means that we're doing a 5 by 5 matrix, an n by n identity matrix. In this case, the input's 5. And we want our range, make another range tensor in which we have torch.a range of 5. And let's make it a float. So what range is doing, we have this 1D vector of 0, 1, 2, 3, 4. And we want to replace the diagonal with that. So identity in range of 5. We're going to equal that to the range. And let's just print like our modified identity matrix. Oh shit. Sorry. I don't know if I ran the. Oh, my bad. First tensor code. Let's see what my issue was. Look at. I'm not sure exactly what I did differently in the code. No. Damn. Let me try rerunning this to see, but some mistake was made along the way. Yeah. Yeah, I don't know, honestly.
If you don't mind me asking, what is an identity tensor? Like, what does that mean?
The identity tensor? Yeah, I'm sorry. Kind of ignore the error for now. I'll figure out where I went wrong. But the identity tensor, if you can think about as a matrix, if you've done, I believe in discrete math, we start off with matrices. It defines kind of an n by n, let's say in this case 3, well, 3 by 3, we have this 3 by 3 matrix. The identity matrix means that we have ones across the diagonal and zeros elsewhere. So here we have 1, in this case 1 0 0 0 1 0. So we have ones across this diagonal. And in this case, when I do torch.i 5, it's the same operation, right? But here 5, so imagine, the dimensionality would be a 5 by 5 matrix. So the ones keep going down, the zeros. Yeah.
So it's just a diagonal matrix.
Yeah.
Oh, okay.
Yeah.
Interesting.
Now, again, apologies for this. I'm really confused by this error because it didn't happen before. Did it happen to you guys? Oh, you guys are getting the same error. Bro.
The error is you're trying to use a tensor as a callable. Sounds like maybe
I get that, but for example, we ran the cell like during this session, nothing happened. So I'm kind of lost on what like made it randomly tick. And I mean, if y'all know the solution, please help me out here? Because
Yeah, what are you trying to do on that line? It says identity range 5. Are you trying to parse the tensor, or you're trying to?
I'm trying to, we have this right here. We have a range, so we have like in this case to fit this it's 0, 1, 2, and I want to place this across this diagonal like this. So then the resulting matrix would be kind of like this, where we have the A range across the diagonal. That's what I try to do there. I don't know here. I don't know why the errors is happening here. Tensor object is not callable for epoch and range epochs. Am I declaring the epochs as a tensor? No. That's super interesting. Let's see if the other code cells run. Yeah. Yeah, so let's jump to 2. I don't know what's going on with 1. We'll revisit this. No worries. Here we're going to work with linspace. We want to create 100 points between -2 pi and 2 pi. And let's just declare torch dot linspace. And remember, the range is from -2 pi to 2 pi. And we're going to do it, we're going to create 100 points. And that's pretty much that. Let's print the shape of this. So you can see we have 100 points across this. And for our third thing, we want to create a 3 by 3 by 3 tensor where each element is drawn from a normal distribution. So basically just, if you remember the rand, like the random, here we have random is equal to torch dot random. And then we put the dimensionality, right? 3 by 3 by 3. And let's print the shape of this tensor. Random dot shape. And it should be 3 by 3 by 3. So again, that's just declaring different tensors. And again, I wish I could.
I have some code here.
All right, because I'm at a loss as to what.
Yeah, so basically you have the identity tensor, and then here you have the center column, and then you basically could flip it and use the flip operation to do just how you're showing.
Yeah.
But that's how.
Gotcha.
There's probably some easier way to do this with INSUM or
Yeah.
reshape or something, but
Yeah.
yeah.
Gotcha. Thank you. I'm at a loss because the same error is also popping up here. I'm not sure why. But let's move on. If we run into the same error again, then we'll work through it. Slicing and manipulation. This was another, if you remember the slicing syntax. And here we have a couple other things. So given a tensor, a 10 by 30 by 3 by 32 by 32 tensor. So again, if we visualize this as images, these are 10 RGB images of 32 by 32. We want to extract only the green channel of the 5th image. So first, let's declare the images as like the Z value that we were given there, right? And to have the green channel, we want to images. So again, we wanted the fifth image, right? Everything is indexed from 0 onwards. So the 5th image would be the 4th index. And remember, the actual dimension that tells us the image would be the batch dimension. We want the green channel. So RGB, green would be the second index. So that would be index number 1. And we want to keep the other ones as is. That's why we use the colon syntax. And to kind of verify that, we can just put like the shape of green. It should return a 32 by 32 tensor. So again, here we're grabbing from this batch of images, we are grabbing a specific channel of a specific image while maintaining the height and the width. And for 2, here we're going to use permute to change an image of shape 3 by 224 by 224, kind of flip it around and have it be 224 by 224 by 3. So let's first declare the image again. We're making kind of like randomizing the image ourselves. So 3, 224, 224. This is us again declaring the dimensionality. And when we permute it, we would do image dot, if you remember, permute. And now what we're going to do is we're going to do this. What this is saying is the dimensionality at index 1, we're going to put it here. The dimensionality of at index 2, we put it here. And then the dimensionality of index 0, we put it to the end. This would reshape, this would permute this differently to be a 224 by 224 by 3. We can kind of verify this with the shapes of the two. So we have permute.shape, and before it, let me do image.shape. Image.shape. There you go. So again, this operation, we're flipping around the dimensions. And for 3, what is 3? Flatten a 4 by 4 by 4 tensor into a 1 by 64 tensor. So we have an OG tensor, it's torch. Again, we're going to use randn to randomly make a 4 by 4 by 4 tensor. And we're going to use .view -1 to flatten it. Here, print the shapes. Here, you see that we flatten this 4 by 4 by 4, 4 times 4, 16, times 4 is 64 into this. We do this a lot when we want to flatten images, let's say after some kind of convolutional layer into our feed-forward layers. And we also did this last workshop as well. And now broadcasting, what we talked about with broadcasting, we're going to declare a 10 by 3 matrix and just a vector B3 to add them. Like, let's just save this into a result. But this is just showing how a 10 by 3 matrix and a 1 by 3 vector, how broadcasting occurs, in which B is kind of broadcasted across all the 10 rows, despite only being 1 row. And before we go into just concatenation and stacking, do like the INSUM. Maybe now it wouldn't make sense, but I mean, over time, it would be cool to like fully learn how to use INSUM. So this is just a little fun exercise. What the goal is, we want A, which is size B and M. Oops, B and M. We want to multiply it with, right? Yeah, we want to multiply with B and P, which is B, that is the shape. And this result would give us resulting shape of B and P. How would this be done in INSUM? First, let's randomize. Let me check, because this was, and sorry, here I'm at M. Yeah, I put this wrong here. My apologies. M. So basically, the batch layers are the same. The batch dimensionality is the same. The second dimensionality, N, is 2. And then in the first one, M is 4. So then we want the second tensor to be BMP, or yeah, P. And then when we multiply them, we want the size of the result tensor to be BNP. So here we're going to use INSUM. Now we're getting spoiled by Gemini, but let's just write it out. BNM, right? So we have the first tensor, size BNM. Put a comma, BMP. So this is us multiplying the two, and the resulting value should be BNP. If we print the shape of this result, that shape, ooh, another error.
This is a concat example.
This is just showing off INSUM.
Oh,
Concatenation, that would just be the last one we do. Now, errors again. What did I do wrong? Right. So here we want to declare that A is the BNM, and then the BMP is B. And our resulting shape is B, which is 5, N, right, which is 2, and P, which is 3. So this is just a little demonstration of INSUM and multiplying with INSUM. Play around with it, see what patterns you find, and if it is more like maybe intuitive for you to use. But yeah, it's very interesting notation, but there is logic behind it. You just need to practice it to see the intuition behind it. And then here we're just concatenating. So let's create 3 tensors, right? 3 tensors of shape. Of shape 128 by 128. So we do T1. Let's just do T2 and T3. So those are our 3 tensors. Our first goal, we want to concatenate them into one tensor of 384 by 128. The notation for that would be concat equals torch.cat, right? And then we group T1, T2, and T3 along dimension 0. Let's print the shape of this. So the shape is 384 by 128 because we concatenated them by the 0th dimension. If we do it by the first dimension, we would get 128 by 384. And by the second dimension, there is none. We get an outer range error. But in this case, we're doing it by the 0th dimension. That's the concatenation. And then the last thing, we want to stack them to get basically a batch of 3 different 128 by 128 tensors. So we get stack equals torch.stack. It's the same kind of syntax, just we're using the stack method. And this is our resulting shape. Try by 1. This just tells us what dimension we're going. So let's do it by 0. And we get a 3 by 128 by 128 stack of tensors. And this is just little intro to PyTorch syntax. I still don't have this figured out, but I'll probably post an update on the Discord if I figure that out, because it caught me really off guard because it was working perfectly fine before this. But other than that little bump on the road, this, you can go back to this, kind of think of it like a little cheat sheet if you're working with PyTorch. The little different methods that you can use, also refer to this over here. And yeah, I mean, that's pretty much what we have in store for today. I'm sorry. Let me know when to move.
oh yeah.
You're good? Okay. And yeah, that's what we have for today. So on Wednesday, what we're going to do is more in-depth backpropagation, and we're going to build our own miniature auto differentiation engine. It will be math heavy, but we will get like a functioning project out of it. It will be really interesting, and it builds the intuition of understanding how neural networks train. So this is the Luma, if you're interested for that lecture. And yeah, other than that, thank you all for coming. Those of you online, thank you. I really appreciate it. And I hope to see you guys on Wednesday. Yeah. Bye, guys. Thank you.